The last topic we're going to look at with valence bond theory is how do we think about resonance structures and what's actually happening with the bonding and the electrons in terms of resonance structures. We've already talked about this, but not in the context of valence bond theory. So let's think about something like ozone. That's our poster child for resonance. It's the one we've used as our example, right? So we know we have this structure here in resonance with this Lewis structure here. Let me include all the correct number of lone pairs on these oxygens over here. Right, so we've seen this structure a few times. And we can describe the geometry here, right? So the electron pair geometry and the hybridization as well. Electron pair is going to be trigonal planar. And we know that the molecular geometry is going to be bent, right? And we can also talk about the hybridization. So which hybrid orbitals are present? And the hybridization, since we have a trigonal planar electron pair geometry, this will be an sp2 set of sp2 hybrid orbitals. So let's draw a picture here over on the right-hand side, where we have one oxygen here, and it's going to form its sp2 hybrids. So that forms that trigonal planar structure. And then the other oxygens are going to have their hybrid orbitals that point out here as well. And we're going to have our lone pair up here. All right, so what's happening here? Well, these are forming our sigma bonds. And we're not going to worry too much about these oxygens on the side, but they're going to have some orbital that overlaps with the sp2 hybrid orbitals. So this figure is getting pretty busy, but we have sp2 or hybrid orbitals here. And we also have sp2 on the other oxygens. That's going to be relevant in just a second. Now, since these are sp2, we still have an extra p orbital. And we know that if we sort of look at one of these Lewis structures, we can pretty clearly draw what's going on. Similar to what we've done in the past, the p orbital is pointing in and out of the page. So I'm going to tilt this ozone molecule on its side. So we're going to tilt it like this. So we'll put the, well, actually, we'll tilt it towards me. So we'll have one oxygen in front, and then each other oxygen atom going back along here. So our sigma bonds are forming along here, and we have a leftover p orbital on this oxygen, and we'll also have p orbitals on these oxygens on the side. Now, if we draw the double bond over here, we would have a pi bond here. And that would be one resonance structure, so if the double bond's on that side. But we have a completely analogous resonance structure. Whoops. Back here, where we can draw the same thing with the double bond on the other side. So again, we've got the ozone sort of flipped on its side like this from how we originally drew it. So it's bent, but it's bent away from us. And we could take the leftover p orbital here and combine it with the p orbital on the other oxygen and form a pi bond on this side. Which one's correct? Well, from what we discussed earlier when we were talking about resonance structures, it should be a mixture of these two. And the real correct structure is that we have a pi bond that goes across the entire molecule. It'll only have 2 electrons in it, so those electrons are shared across 3 atoms, and that's what's really the correct way to look at this in terms of valence bond theory. So our 3 p orbitals are going to combine to form one giant p orbital over the top and bottom. There's still only 2 electrons to put into this, so it's still just 2 electrons shared, but we get a pi bond over 3 atoms. Now, it may be a little bit hard to follow this visually, so I've got some alternative views that we can look at, not of ozone, but of a slightly different molecule here. Yeah, I want to be able to draw on it. So I'm just going to grab those pictures that flashed up on the screen for a minute. So we're going to look at nitrate, NO3-, which has a similar thing. We have a resonance structure. Well, let me just draw the resonance structures of nitrate again. It's something you've seen, but I'm going to leave off the lone pairs on the sides. But it looks like this, and we can do double bond in any of the positions here. There are lone pairs on the oxygens. I'm just leaving them off for speed and clarity. All right, so this is what we have. And we can draw one of the resonance structures. Got this picture here. I gotta make it bigger so you can actually read what it says here. And make sure I don't put it behind my face. All right, that should be good enough. Put this back to full screen. Okay, so what are we looking at here? So this is a different depiction of exactly what I was trying to show in the previous example with ozone. So our nitrate, all right, here's our nitrate, and we flip this on its side because we're looking at the same sort of hybridization. So if we look over here, these are sp2 hybrid, right? Because they all form trigonal planar structures. So there's a leftover p orbital, and that's true on not only the nitrogen but also the oxygens. And if we're thinking about just one resonance structure, this is the sort of picture we'd have in terms of valence bond theory. There's sigma bonds here that we're not depicting on this picture, and then there's a pi bond where the double bond is. That's, again, above and below the internuclear axis, like all pi bonds are. But what really happens is that is not specific to that NO bond. It spreads out across the entire molecule. And so what we get is this picture down here, just like with the ozone, where this pi bond spreads out all across the whole molecule. And we get this pi cloud both above and below the molecule. And this is what leads to all these bonds being equivalent, as we talked about. There's sort of like 1 1/3 bonds because this second bond gets spread out across the entire molecule. So in terms of the resonance, what's happening is that, drawing the bonding, the hybrid orbitals in terms of just one resonance structure doesn't tell us the whole picture. We actually get this spread out across the whole molecule. I think one of the coolest versions of this, and one that is relevant in organic chemistry, is benzene. So we've also talked about benzene as an example of resonance. And so that's this molecule here, just as a reminder. I'm going to use organic line drawings. So we have carbons at all the vertices here, and then alternating double and single bonds. So this is, with line drawings, the structure of benzene. Just as a reminder, there are hydrogens at each of these here to create 4 bonds with every carbon atom. Okay, so we have a sigma bond framework. Each of these bonds here, these are all sigma bonds. So between the carbons and the hydrogens and the carbons and the other carbons, there's one sigma bond. And the way it's drawn here is we have pi bonds. Now, if you draw just one resonance structure, you're going to get something that looks like this. So you have localized pi bonds where it's not quite drawn the same way I have it here, but you have your double bond here, so your sigma bonds are forming this hexagon, and then your pi bonds are looking like this. But you can draw a resonance structure where you switch where the single and double bonds are, right? So we can draw a resonance structure where these double bonds all shift over by one position. And what that would look like in terms of pi bonds would be the structure right here. We switch where the pi bonds are. And the real picture is that we get what's in the right-hand side here, where everything is delocalized. The pi bonds spread out around the whole ring of the benzene molecule. And this is the consequence of benzene is a very stable molecule, and its structure shows up a lot. And this is what's actually happening. The electrons spread out, and we can visualize this as pi bonds that spread out across the whole molecule. So this is another way of understanding what we've already talked about in terms of resonance, that the electrons are shared across the entire molecule rather than being localized into individual double bonds. And so that's the idea. That's the last part we're going to talk about in terms of valence bond theory. we can understand resonance and understand this delocalization effect. When there's resonance structures in a molecule and there are equivalent resonance structures, that will lead to the stabilizing effect. Things with resonance structures will have a little bit lower energy and be a little bit more stable because these electrons can spread out across the whole molecule. So that concludes our section on valence bond theory. And we have one more topic in Chapter 9. We're going to talk very briefly, not go into a real in-depth discussion, as much as I'd like to, but talk about molecular orbital theory. One, sort of like the next layer, the next step up in understanding how atomic orbitals become bonds in molecules.